Hello, my name is Non Janescu, and today I will be presenting the work of Team 2, the Water Skimmer. Located on the central Atlantic coast of Florida, the Indian River Lagoon stretches over 156 miles and across 5 different counties. The lagoon is connected with the Atlantic Ocean at 5 different inlets and is slightly brackish but primarily freshwater. The lagoon borders some very interesting locations, including the Kennedy Space Center and even the FAU Harbor Branch campus. Home to more than 4,300 plant and animal species, the lagoon is one of the most biodiverse ecosystems in the entire northern hemisphere. Currently, 48 species stand as being endangered in the lagoon and is actually the only home for Atlantic saltmarsh snakes in the entire world. A small example of unique and interesting species home to the lagoon include red mangroves, manatees, dolphins, and roseate spoonbills. Currently, the Indian River Lagoon is under threat from non-centralized pollution, leading to diminishing water quality and resulting algae blooms. These effects greatly destabilize the natural ecology of the ecosystem, damaging the quality of life of all species and further leading to fatalities. The source of these pollutants is hard to pinpoint and can be attributed to any number of factors such as fertilizer runoff, septic tank seepage, polluted stormwater, and many other micro-factors. Researchers and conservationists working on repairing the river are struggling. It is hard to decisively remove all the factors. Leading figures would show that currently the lagoon has lost approximately 58% of its natural seagrass due to cloudy water. This has led to mass starvation and decrease of the native manatee population, further endangering the species. This is further complemented by massive fish kills from low oxygen levels in the water from the invasive algae. Concerned with the current status of the Indian River Lagoon, our group has set out to develop a research tool for gathering water quality data to further aid conservation efforts. Through research, we found multiple water quality monitoring systems currently in use today, such as the Orca Kilroy. While effective in gathering essential data, we found that this system was highly limiting as it was a stationary unit and unable to pinpoint exact locations of incoming contaminants. Understanding these limitations, we set out to develop a craft capable of demonstrating similar water quality monitoring, but on a moving platform. This would allow operators to monitor more riverbank over extended periods of time, developing numerical trends and pinpointing locations of incoming contaminants. Set on making this an effective research tool, we applied multiple system requirements to the design objective. A large focus was applied on keeping the craft fully wireless and able to be controlled and monitored over long distances. Over the designing process, our craft has gone through multiple iterations and design changes, including different propulsion and steering methods, various sensor types, and the general shape of both the deck and hulls. Through trials, we have concluded the final design and have begun constructing. This model entails a dual hull catamaran style for stability, dual propellers for both propulsion and steering, 4 data collecting sensors, a camera, and an accessible electronics box. The primary focus of the design over the others was to keep all the moving parts above the waterline so that they are not obstructed by water-based debris. The current build model is not fully complete, and the necessary steps to complete the craft will be covered later in the video. The fabrication of the craft can be broken down into 3 primary parts: the motor and deck mounts, the hulls, and the deck and electronic box. The mounts in the system are all made of aluminum and went through many fabrication steps, including cutting, sanding, milling, water jetting, and painting. Following the fabrication of the mounts and deck, we began constructing the hulls. The hulls of the craft were a highly intensive section to build and went through many steps and trials. First, we used the water jet to create a drawing-accurate foam molds. Second, we layered them together and began sanding them down into their smooth shape. Third, we epoxied them together to keep a tight bond between the layers. Fourth, we covered them with a layer of Bondo to create a hard shell and keep the shape of the mold. Fifth, we began applying layers of fiberglass, and then used power tools to shave excess fiberglass from the mold. Lastly, we applied layers of gel coat, with final things of sanding and then buffering to reach the current state of them. Installed on the craft are 2 different sets of sensors. The first is the data collection set, including a turbidity sensor, ultrasonic sensor, anemometer sensor, and temperature sensor. These are the primary data collection units, and all of the numerics will not only be saved on an onboard SD card, but also live transmitted to the operator. The second set of sensors are for general safety and tracking of the craft. These include the GPS tracker, water detection, onboard camera, and a 9-axis gyroscope. This will also be saved onto an SD card and also live transmitted to the operator. Additional important electronic components include an Arduino Mega, a Raspberry Pi, both a 12-volt and 5-volt battery sources, a battery monitoring system, an RC remote, custom PC board, and a motor controller for the 2 motors. Our electronic system is broken into 2 sectors, the 12-volt battery and the 5-volt battery. The 12-volt system powers the main propulsion units, which are 2 1000 kV brushless motors and the anemometer sensor. The 5-volt system powers the bulk of our electronics, including both the Arduino Mega and Raspberry Pi, and all of the following sensors: camera module and 40mm vent fans. As our prototype is currently incomplete, there are several things that we need to continue working on to complete the project. Some of the fabrication work includes completing the holes, installing a few 3D printed parts, and working on the latching mechanism of the electronics box. As for electronics, all of the sensors have been tested, but now we need to unitize the full system and get them to work together. Furthermore, installing all of those electronic systems into the craft. When all the bits and pieces are assembled, we can begin running full system tests and finalizing any kinks and issues. We believe that the water skimmer brings value to the market as it is a unique piece of technology in its field and one-ups current deployed methods. Our current prototype is an example of operation and stands as a base unit for future modifications, such as different sensor types and the inclusion of higher-end electronics and software. Such electronics and software can include things like autonomous function, solar panels, larger motors/batteries, and much more. With nearly endless modifications and additions, the water skimmer is a desirable platform that can be used to improve water monitoring systems around the world. Any number of companies, foundations, and governments could make good use of the water skimmer. When examining the Indian River Lagoon specifically, any number of the 5 bordering counties' local governments could be interested, along with the primary foundation currently monitoring the lagoon, One Lagoon. On behalf of the group, we would like to thank you and everyone supporting us through the design process. Continually extending a thank you to the College of Engineering and Computer Science, Office of Undergraduate Research and Inquiry, and the FAU WAVE program for funding this project and making this all possible. Thank you.